At this time, I would like to introduce our next keynote speaker, Dr. Matt Wood from Amazon. Dr. Wood is part of a technical leadership team at Amazon Web Services. He brings expertise in distribution systems, architecture, web-scale analytics, big data, machine learning, and performance computing to build sophisticated applications that help customers bring their new ideas to life through technology. Ladies and gentlemen, Dr. Wood.
Thank you. Appreciate it. All righty. Good afternoon, everyone. Can you hear me at the back? Give me a wave if you can hear me at the back. Lots of waves. OK, fantastic. So good afternoon. My name is Matt Woods. I'm the general manager for artificial intelligence at Amazon Web Services. I get involved in pretty much everything that we do at Amazon as it relates to data. And today I'm just going to tell a couple of stories about some of the things that I've seen, field notes from expeditions with data. So some of the things we've done with machine learning, some of the things we've done with big data analytics, and some of the ways that we use data at Amazon. This always seems to get left to the end, but thank you. It's really a privilege to be here today to tell you a little bit more about what we're doing in Amazon. And I've had some amazing meetings already today so far, so thank you for the invitation, and it's a privilege to talk to you all today. So I'm going to talk today primarily about data. As I'm sure all of you are aware, it's never been cheaper to generate more data. And so the economics are now favorable that more data is being generated all the time, whether it is from tactical deployments, whether it is from internal applications, whether it's even health data. More and more data is being generated all the time. And this causes some concerns. It introduces some complexities, primarily because there's more data being generated. There's lots and lots of data. And once you start having lots of data available, typically you want to be able to use it in lots of different places. And once you have it available in lots of different places, lots of different people want to use that data and access that data. And certain members of that audience will be able to access some parts of it, some of it will be able to access other parts of it. And as another element, more data and more places and more people begets more and more uses of that data. And it's very difficult to guess up front how you want to use that data when you're even just collecting it. And of course, there's one other dimension that a lot of you will consider, and that's cost. You want the cost of this to be as small as possible. So all of these elements coalesce into creating an enormous amount of complexity as it relates to managing data and actually using it for something useful. And this really becomes a problem when you're still working on on-premises infrastructure. With on-premises infrastructure, the walls of the data center, they can't move. And so you're stuck with the resources that you have available. You've got a certain amount of storage, you've got a certain amount of compute, you've got a certain amount of analytics capabilities, and so you end up starting to have to frame the problem or the question you want to ask of your data inside of those resources. I call this inside-the-box thinking. You're literally having to think inside the box of your data center. But of course, in the cloud, where your data center walls can move, you can provision as much storage as you want. You can collect as much data as you want, and then you can analyze that with a very rich set of tools and answer any question that you want. And so the constraints of the old world, the constraints of having to manage and collect and store this data inside a box, just start to melt away. And what that means is that customers can do more and more and more with that data, with more people involved across more places, and drive a lot more innovation using their data. So there's a couple of different stages of working with data. The first is you want to be able to collect it. And AWS has a very wide range of services for collecting data, everything from just a direct upload into the cloud, all the way through to direct connections to our data centers, which give you dedicated and private connectivity up onto AWS. But in some cases, you should never underestimate the bandwidth of a FedEx truck. And sometimes you've got so much data that you want to be able to move it using physical media. So we have a physical unit, which we call a Snowball, where you can order one of these. They're about $150 per month. You can load your data onto it, ship it, close it all back up, and just ship it back to us, and we'll load up data more quickly. Customers love these things. We saw unprecedented demand after we announced them, so much so that they send us selfies. So here are our Snowball selfies. And I include these deliberately to encourage you to send us more. I love these things. Look at that guy on the bottom left. If that isn't bringing customers joy, I don't know what is. A Snowball will move about 50 to 80 terabytes in a single device. And that means that you can move, in the real terms, petabytes of data using this system. But we do have some customers that want to move exabytes of data up to the cloud as quickly as they can. And that means managing about 10,000 of these itty-bitty devices, which is cumbersome and time-consuming. And you'd be surprised today how many customers of AWS have exabytes of data, including some people in this room, I suspect, that they want to move up into the cloud. And so last year, we made available some real out-of-the-box thinking when we introduced Snowmobile. Snowmobile is a 100 petabyte data container. We'll drive it up to your data center. You open up the back doors. You plug in your fiber. You plug in power. You just start to load the data in. It takes about 6 weeks to load 100 petabytes onto the device. You get 24/7 security of the device when it's on site. Once it's full, we'll come pick it up with the tractor trailer, drive it to the AWS data centers. It takes about 6 weeks to load it back in, and you can keep rotating these round and round and round to collect more and more data. So this is for moving exabytes of data at a time, and we have a huge number of these driving around the US even today. When you've got it up there, you need to be able to store it. You want to be able to store both the raw data, you want to be able to transform that data and load it into databases. And AWS has a very broad range of services that allows you to run the right type of database and the right type of storage for your workloads. And then once you've got it stored, you want to be able to analyze against it. And all of those different analytics workloads look and operate a little bit differently. And we provide, again, a broad set of analytics capabilities, whether it is traditional reporting and data warehousing or ad hoc queries against petabytes or exabytes of data. We recently ran a benchmark against an exabyte. I'm obsessed with exabytes. It's just such a nice number. We ran a query against an exabyte of data. It was a complex query, lots of different joins, the sort of production query that we see inside Amazon. And using our latest system, which we call Spectrum, we got a result back in 155 seconds. So we were able to analyze this data at incredible volume with such complexity that we now don't think inside the box. We start to allow the data to tell us. We're able to explore the data at any scale, and we're able to ask questions of that data without any constraint. Ask the real questions which are going to drive real material change for our organizations. And so I'm going to just focus in on 3 different areas now. I'm going to talk a little bit about machine learning and data. I'm going to talk a little bit about what you do with data if you're operating in a disconnected environment, how you collect and process that data, even in a disconnected environment. You won't necessarily expect to hear a cloud computing company talk about disconnected environments, but I'll talk a bit about that. And then I'll wrap it up with a discussion about how we use data inside Amazon, just for a bit of color to see how we do it inside industry. So I want to start my story with the humble Rubiks Cube. I'm sure you're all familiar with this. This was the toy of the year in 1984. It's a series of colored blocks. You swivel them around, and the idea is you want all sides to be a similar color. And the question I want to ask is, how do you best solve a Rubik's Cube? How do you program a computer to solve a Rubik's Cube for you? So there's a couple of different approaches you could take. The first is you could code a series of rules. If you see this combination, then take this series of rules, this series of moves to go build the solution. This, by the way, is the singleton nomenclature. It tells you how to solve a Rubik's Cube in a concise format. But the challenge with this approach of writing down physical rules is the computer will never be better than you at solving the Rubik's Cube. And I suck, so it's not going to be very good. So this isn't the right approach. Alternatively, you can try and enumerate every single possible combination of the Rubik's Cube and then search your way through every possible combination to the solution. The challenge with this is, just with a simple Rubik's Cube, a simple toy, there are 43 quintillion combinations. That's the real number. That's a lot of zeros. And if you were to try and solve this, you have to sample every single one to see if it's the right approach. Now, some crazy people actually tried to do this. They wrote a computer program which sampled all 43 quintillion combinations, and that computer program ran for the equivalent of 35 years. That is a huge amount of time to wait and requires a huge amount of computational resources just to solve a Rubik's Cube. Now, you can imagine the complexity of something like autonomous driving, autonomous unmanned vehicles. The degrees of freedom there are so much greater, and the complexity is so much greater that you can't solve it this way. So this doesn't work either. Instead, what you could do is you could build a learning system, something which learned by examples just like humans do, modeled on the human brain. So you could take a known Rubiks Cube configuration and a known solution, and you could introduce it to the learning function. And every time the learning function saw a new combination, it would learn a little bit more. Now, to start with, just like humans, like when we're trying to walk, it's not going to do a very, very good job. It's going to have a low degree of accuracy. But the more data and the more examples you give it, you're going to start to see improvements. You're going to start to see that accuracy improve. To the point where, if you show it hundreds of thousands of examples of inputs, and hundreds of thousands of examples of outputs, eventually it's going to be able to discern and learn how to solve a Rubik's Cube with a very high degree of accuracy, much better than I could ever do it by teaching it a series of rules. And that means that if you introduce something it hasn't seen before, it's going to take a pretty good guess at what the solution might be. And this is the basis for machine learning. And it shows you just how sophisticated machine learning can get when you can solve a Rubik's Cube, not just in 35 years, but a little bit more quickly. So let's take a look at, this is a machine learning-driven Rubik's Cube solver. 0.9 seconds. You want to see that again? Okay. There it is. So this is a series of cameras which are looking at the Rubik's Cube in real time, and they're using machine learning to solve it. And there's a lot of actual smarts actually in just turning the cube, and a lot of machine learning on the device down there, just turning the cube and manipulating it at that sort of speed. This makes everybody very happy. And it allows you to solve problems that you may not even know how to solve yourself. Machine learning is experiencing something of a renaissance at the moment. And it's primarily because a lot of the primary challenges that have held machine learning back in the past, we're starting to overcome them. And they almost all revolve around scale. Machine learning requires very, very large amounts of data. The more data you give the learning model, the better it performs, usually. It requires a large amount of compute requirements, typically expensive GPUs, to actually run all of that training. And prediction is very challenging as well. It's very computationally demanding to infer predictions against those trained models. But at AWS, we've been solving challenges like this for customers for well over a decade. And we have customers that we've already seen that have exabytes of data up on the platform. And they're migrating as much of that data as quickly as they can up to AWS. In terms of training, we have the latest and greatest GPUs available on the platform. And for inference, we have GPUs and CPUs. You want a choice of both, depending on the cost. And we even have customers that are using serverless models like Lambda to be able to go run their machine learning without having to worry about any of the infrastructure under the hood. So I wanted to give you some examples of some of the work customers are doing. One of my favorite ones is work that Stanford did on trying to provide early detection of diabetic blindness. Diabetic blindness is one of the leading causes of blindness for men in the US between about 21 and 46. And the way that you detect it today is by looking at microvasculature changes in the back of the eye, using an image like this, which is a fundoscope. And so we worked with Stanford. We took pictures of healthy eyes, we took pictures of unhealthy eyes, and we built a deep learning model to be able to distinguish the difference. And we're able to detect and, in most cases, prevent diabetic blindness in 95% of cases. We also see regulated workloads starting to use machine learning, FDA medical imaging, for example. This is all trained and run up on AWS. This is a sagittal MRI section through the chest, and you can see that the system there is detecting a tumor up in the right-hand corner. So this isn't about machines taking over from people. This is about a machine learning model providing diagnostic support to a radiographer, making their lives a little bit easier, making their time a little bit more useful. We see consumer uses as well. This is Wolfram Alpha. It's a computational knowledge engine, which is a very grand name for what is just a question and answer system. So you can ask Alpha any question that you want. You can see here I've asked it, who recorded my favorite album, Pet Sounds? And the system understands that Pet Sounds is an album, and it knows that that album has an artist associated with it, and it returns the Beach Boys. And when we talk about the challenges of running and inferring predictions against complex models at scale, some of you may be familiar with Alpha. It's because this is what Siri hands off to when Siri on the iPhone doesn't know the answer. So this is the sort of scale you need to be able to run at when you have billions of devices, being able to fire any random question at you that Siri can pass off to. We also see a lot of machine learning use in public safety. So Motorola Solutions are doing some really interesting work in missing persons. So they are able to save thousands of man-hours from just reviewing surveillance footage automatically. And instead, they can build a private directory of missing persons and just have the system automatically detect. Same with the Washington County Sheriff's Department over in Oregon. In 3 weeks with one developer, they were able to take surveillance footage, build out a private catalog of 300,000 persons of interest, and within 1 week of that system going live, it had attached and triggered and had identified a cold case which led to an arrest. So what we're talking about here is a differentiating set of capabilities which we're trying to put in the hands of as many developers as possible. For all the good they do in their community, the Washington County Sheriff's Department are not well known as a technical leader. They're not at Amazon, they're not at Facebook, they're not at Google, they're a police department. And they're still able to use these services quickly and easily with very, very low investment to advance their mission. We also take machine learning that we do internally and make it available on our customers' data. We have a new service which we announced about 3 weeks ago, which we call Amazon Macy. And Macy takes a look at the data that you have stored in the Amazon cloud, and it automatically, using machine learning, classifies that data. It looks to see if you have something which is a low risk of a leak, something like a web page, which is already public. That's very low risk. All the way through to personally identifiable health information, credit cards, and social security information, which is considered highly valuable and which you don't want to leak. It then indexes all of that information, and it lets you know if any of that data is available and is publicly accessible, or is available to anyone who shouldn't have access. And in addition to that, it routinely learns and monitors how individual users access that data. So an example I told in a meeting earlier was that we had one customer, a large financial services customer. They had an HR team, and the HR team almost always accessed HR information. However, they had their accounts compromised, and as a result, they were able to log in, use that account, and they started to access different types of information, different operational information that wasn't usually accessed by that account. Macy immediately identified that this was not normal behavior, and it stopped access to those two accounts immediately, preventing access to all of that data because it was erroneous, and then flagged it up to the customer for further investigation. So this means you get to gain visibility into globally shared content as you're sharing all this information globally with as many people as possible to allow them to innovate on top of it. You still want to know which information is being shared and with whom. You want to be able to identify anomalous access. So if somebody is all of a sudden accessing, or an employee who's just been dismissed starts downloading everything, you don't want that to happen, and this system will identify that automatically and turn it off. And it also allows you to implement continuous compliance. So this isn't just a point-in-time snapshot. It's continually learning, relearning, and reevaluating your compliance rules against the data that you have stored in AWS. And all of this is available today on AWS. So that's a little bit about how we use machine learning. I want to talk a little bit about data and devices. There are some increased challenges in doing data analytics and machine learning at the edge, or at the tactical edge. In no small part because the volumes of the data that are collected can be very, very large. In some cases, the latencies required to send that data back to the cloud can be very unfavorable. You don't want to have to wait for a couple of second round trip to the cloud in order to be able to process that data, even if you can do it at volume. And in most cases, you want all of this to continue to operate in disconnected environments. Just because your communications gets interrupted, you don't want all your machine learning and data analytics to stop working. So to address this, we have a service which we call Amazon Greengrass. The grass is just as green on the other side. This allows you to basically deploy a mini version of AWS inside devices which you run at the tactical edge. And it allows them to collect and analyze data in real time, just like you do on AWS, but without that data having to stream back to the cloud. It allows you to synchronize the data and the state of the device in connected or disconnected environments, or environments when connectivity is dropping in and out. And it takes the exact same programming model as we use in AWS and deploys it onto connected devices. So you get all of the benefits of AWS, and you get to deploy them in tactical units at the edge. And I'll give you an example of where we did this for you. This is our Snowball device that I mentioned earlier. It's the latest iteration, which we call Snowball Edge. And not only does this collect data, but it also has onboard compute. And so you can take your same analytics and machine learning workloads and deploy them directly onto this device. As you can see, it's ruggedized. It's waterproof. We've done some testing, which I'll show you in a minute, to military specs. It holds 100 terabytes of data transport. You can pull multiple ones together and cluster them, so you can load more and more data onto them. You can see on the top there, that is an e-ink display, a lot like a Kindle, and that's the shipping address. It's the shipping label to get that device back to AWS. It's stored underneath a locked container, and the reason for that is shipping labels come off. If you're trying to ship something and the shipping label comes off, now you have no idea where your data is. But here, because it's an e-ink display, number one, we automatically put the right address on the place so you can't write it incorrectly, but also it can't come off because it's underneath a locked display. If you open that up, it's got everything that you need to be able to run it. All the power cables are self-contained inside the lockbox. And if you flip it round, you can see all the ports on the back there. And if you open up the other end, then we have another touch screen in there to allow anybody to be able to start to deploy and configure these directly in the field. So with a very small amount of training, these things can be configured in the field. They can collect data from sensory networks. They can do the analysis directly there, and you can either send the results of the analysis back to the cloud over Wi-Fi or over its 4G connection, or you can wait for it to fill up or just pick it up and take it with you when you leave. Importantly, all the data on these devices is encrypted, and we don't store the keys on the device. That means that if something were to happen to this, if at any time when the power is interrupted, we delete the keys automatically, and this thing is just a brick. So if you need to get out of there quickly, just unplug it, leave it there. The data will be completely useless if anybody does get access to the physical drives. We've done some testing. Inside that little barge is a couple of snowballs. We did some barge testing. We did some depth charges around this, and we passed the mil-spec tests. And this allows you to not just collect data, but also process data in real time at the edge. And so this is an example of an autonomous driving system, which uses some of these techniques. So this is actually the best performing autonomous driving system out there at the moment. It's from a startup that's based in San Francisco and over in Beijing. And you can see here the car navigating safely the streets of Beijing, doing object detection. So over on the left-hand side, you can see it identifying all the different cars, the stop signs, all the different people, stopping and navigating safely. And the system can do this not just during the day, but also at night. And it's a much harder problem to solve at night because you have much less information to work with. So there you are, you see it turning onto the road there in Beijing, identifying all the different areas. Somewhat less impressive, but just as important, they're able to do per pixel segmentation down on the device. And in this case, the device is a car. So this is what traffic looks like in Beijing, if you've never been there. But what it's doing here in real time is evaluating every single pixel on an HD display, on an HD camera, and deciding, is that pixel road or is it not road? And this is very helpful because it allows you to identify what is the car, it aids with object detection, and it allows you to identify all the road markings which are down on the road. So all this is happening in real time. And if you pull all of this together, if you pull together the object detection and the per pixel segmentation, you can start to position the car in 3D space just using the vision systems. This is a system that they rather unfortunately call SLAM. And you can see here, the car driving around on the top there, you've got segmentation of the road, object detection, and then a heat map of how far away the objects are to the car behind them. So this is an incredibly sophisticated deep learning system which is trained up in the cloud, but deployed down onto the device to work in a disconnected environment. You don't want your centimeter accurate positioning systems to stop working just because you lose cell signal. So that's data and devices. Finally, I want to wrap up with a discussion about data and Amazon. So some of you may be familiar with this. This is our, what we call the gateway page, the home page on Amazon.com from 1996. You can see we have the old logo, but the new name. As I was explaining this morning, the company was originally called Cadabra, as in abracadabra. But when someone phoned up to register the trademark, the person at the other end of the line misheard it as cadaver. So changed the name. So we have 1 million titles, all books at this point. But you can see even back then in 1996, The third item down there is a system called Eyes and Editors, which is a personal notification service. And this is a machine learning-driven recommendation service. It was our first use of machine learning all the way back in '96. And it made a machine learning recommendation for other titles that you might like, which then went to a human, and that human automatically evaluated and curated it, and then sent out the notification over email. And since then, we've applied machine learning to basically every aspect of our retail business, every aspect of our devices business, every aspect to our cloud computing business. This is a very, very high description of what happens in fulfillment. So the first thing we need to do when we start to fulfill orders is we need to stow those objects. So inventory which we have acquired, which we've paid for, or come from third parties, we need to pull into our distribution network, sit in our fulfillment centers so it's ready when someone orders it. Then someone makes the order on the website, at which point we have to pick it back off the shelves and then fulfill it back to the customer. I'm going to talk through a little bit about how we use machine learning and data throughout all of these areas. The first is with stowing. So this is an onboarding system. If you've ever been to one of our fulfillment centers or if you've ever seen it, these are very, very large million-square-foot facilities. They're extremely expensive to build. And so in order to get the right return on investment and keep our prices low, we need to get as much throughput through these distribution centers and fulfillment centers as possible. That means two things. Number one, making sure that we get inventory in quickly, and number two, making sure that we get it out quickly. So previously what we had to do in our previous generation fulfillment center was we had lots and lots of people, as you see here, validating the inventory that was coming in. So if we had bought, say, 10 iPads, someone would have to open the box, they'd have to count the iPads, they'd have to make sure the iPads were the right capacity and the right make and the right model, and then they would send it off to be stowed so that a customer could actually buy it on the retail site. This process used to take hours for an individual item. Instead, in our new generation facilities, we use a computer vision system. So you can probably see, just in amongst all the boxes and all the chaos here, cameras hanging down. And these cameras are used to automatically evaluate what's inside the box. So all an associate has to do is stand, open the box, take a step back, and the vision system looks down and evaluates if we've got the right widgets in the right box. Assuming everything is okay, it goes into automated fulfillment. If not, then it goes into a manual exception. And we decrease the time from hours down to less than 30 minutes to onboard new inventory. And that's really important at peak times like holidays, or as I'll talk about later on Prime Day, which is our busiest shopping day. Data is used across the entire website for customers who are searching and discovering. You may be familiar with customers who bought this also bought. That's all powered through data and machine learning. And once customers actually make their decision, choose to order a book, in this case a Harry Potter book, then we have to go back to our inventory system, extract and pick the item, and then put it in a box to be shipped to a customer. Here we use as much automation as we can to make that process as quick as possible. These are our Amazon robotics systems. They help with moving inventory around our fulfillment centers. So here they are. I don't know if you've ever seen these. It's super cute. So these have command and control up on AWS, but they also move autonomously around. Here they are lining up for duty. And they can pick up about 750 pounds of inventory on 8 to 12-foot stacks and move it around. Now, there's two advantages to this. Number one, we don't have to leave gaps between the aisles where people would have to walk to pick all of their items. That means that we can increase the concentration and get a better return on our fulfillment centers. Second, it's just much more efficient at finding things, because we use these robots not just to organize inventory in the back office, but to bring inventory to people. So here it is scooting around. And what these robots do is they bring the inventory to a person, and that person then picks out the relevant item for a particular order and puts it in one of those yellow trays to go off to fulfillment. Interestingly, we do have a regular annual student challenge to try and replace this person as well. Picking items at Amazon is extremely difficult because of the diversity of the inventory that we manage. And having a robot that can pick up something like a CD, but can also lift something like a waffle maker, is very, very challenging. This is what the students look like this year. Total chaos. But their robots were extremely effective, and a lot of the ideas that come from this actually go into improving our robotic fulfillment and stowing and picking back on Amazon. I'm not sure if you're familiar, but Amazon has a couple of airplanes. This is Amazon One, our first Prime Air flight plane. It doesn't really have anything to do with data. I just couldn't resist putting it in the slide deck. It's a beautiful thing. Okay, so I want to talk a little bit just in the last 10 minutes about how all of this comes together. So we have a lot of work, a lot of customers, we've got a lot of inventory coming in, we've got a lot of customers ordering, we've got a lot of customers that we've got a lot of shipments going out of fulfillment centers, and all of this is running, don't forget, on top of Amazon Web Services, with all the real-time data analytics and all the machine learning that we talked about, driving everything from the robots to the recommendation systems to the transportation network at the other end. And all of this really comes to a head with Prime Day. Prime Day is our busiest our busiest day in retail of the entire year. It eclipses the holiday period, it eclipses peak period, it even eclipses Black Friday. And so I want to talk a little bit about our most recent Prime Day and talk to you a little bit about some of the numbers and the metrics that we saw on that day, to try and paint a picture for what you can do when you invest in this level of automation and what you can do if you invest in this level of data analytics. This data has never been shown anywhere else. You are the first public audience to look at these numbers. I got special permission just for you guys. This is what the traffic to the Amazon website, to the Amazon.com homepage looked like. Actually, all web traffic. For Prime Day 2015, you can see it, just the little blip there over on the left-hand side. Somewhat successful, but some problems with the quality and diversity of products, I think it's fair to say. We learned a lot about that. You can see holiday season 2015, a much broader peak there. And then you can see Prime Day 2016 over on the right-hand side there, much more pronounced peak. What's interesting about this is if we were having to actually buy and provision the hardware to run this, it would be ridiculously expensive, to the point where we probably wouldn't be able to run Prime Day, because we'd have to over-provision against the peak, not the curve. And so we'd have to look at the peak for Prime Day 2016, bump it up by 10 to 15%, and that's the infrastructure that we would be running for the entire year. And that would be a whole bunch of servers not serving, a whole bunch of disks not spinning, a whole bunch of wasted capital, which we would much rather spend on lowering our prices. So how do we do? Well, the first thing is we learn between 2016 and 2017 some tricks of the trade. How can we run this most efficiently? First thing was we audited all of our service teams inside Amazon. We at AWS went around all of our dependency teams, all of our partners across the retail arm, and asked them what they thought their capacity was going to be. How are they judging success? Are they looking at page load time? Are they looking at page numbers, page loads per minute? Like, how are they thinking about the success? What's going to trigger them to need more capacity when they do need it? And so we went around literally hundreds of different service teams inside Amazon to get their input into the capacity we thought they would need. Then we ran a game day. Game day is where we tested all of our assumptions. We basically ran a simulation of the traffic that we were expecting, and we tested all of the metrics that we collected from all the different service teams and deliberately introduced failures. So this is a dry run, basically. This was useful for two reasons. One, it tested to make sure that we were operating as we were expected to on Prime Day. And the second was it built muscle memory for all the operations and all the engineers folks that were actually going to have to respond to challenges in real time when Prime Day went live. Prime Day this year lasted 30 hours. The third thing that we implemented was a war room. This was basically a fancy name for a conference call, but it had hundreds, if not thousands, of people on it at any one time. And this was our single point of coordination for fixing all the different challenges as they became apparent in real time as Prime Day was really happening with customers. So how did it go? I'm going to cover three different metrics. In just Amazon usage, just on Prime Day, Amazon used 52 petabytes of storage on our storage service, and they were handling 835 million I/O requests. So that's every read and write to individual disks. And you can see the growth there year on year. And I find it hard to conceptualize these numbers. A petabyte is so large. But this roughly equates to 676 years of HD video, which was being stored just for those 30 hours. In terms of messaging, messaging is what keeps all of the site components coordinated. All of the different pieces that build the detail pages, every single click, swipe, every single scan of inventory, every single computer vision system, every single machine learning inference is driven through a message. And so we did 102 billion inbound over the period of Prime Day, 217 billion outbound, and we were processing 3 million requests per second. This is very, very large numbers. They're astronomical, to the point where if you count them all up together, they're roughly the same number as 3 times the number of stars in the Milky Way. So this is a very, very large number of requests. Perhaps the biggest success story was a database service that we have called DynamoDB. DynamoDB is the back end for every activity for Alexa, our personal digital assistant, on all devices, Amazon first-party devices and third-party devices, the retail store, and all of our fulfillment and supply chain. It managed 3.34 trillion requests over the course of Prime Day, at a peak of 12.9 million requests per second, up 230% from Prime Day 2016. And so this is, I think, probably the largest distributed system ever deployed in production, with the highest throughput of any system ever deployed into production. To try and contextualize this, I wanted to talk a little bit about a rather peculiar tradition we have at headquarters in Seattle. In between all of our urban campus buildings, Amazon HQ, we have a community banana stand. This hands out bananas to anybody that walks past. It's where I get my breakfast most days, to both Amazon staff or anybody else inside the community. And if you think of every single one of those requests as a banana, and you think about the size of banana stand you would need to go hand out those bananas over the period of Prime Day, you would need a banana stand which is roughly 950 times the size of, well, one of your favorite sporting stadiums. So this is an enormous amount of data and an enormous amount of requests managed in a very small time. So that's kind of interesting, but Prime Day also drives a ton of improvements on the services under the hood. And because we operate these as a managed service, you immediately get access to all those improvements. Also, I wanted to put into context the traffic for Prime Day all up. So this isn't just Amazon traffic, this is all traffic to DynamoDB, the database service, for the last year. And you can see a steady increase there, a bit of a peak over the holidays at the end of last year. And you can see Prime Day there over on the right-hand side. So you can see Prime Day was, at the time, our largest, busiest day on DynamoDB. But just a couple of weeks later, organic growth on DynamoDB meant that we were handling Prime Day traffic or greater just every single day on DynamoDB. This was just a matter of course for us now. And this drives a huge amount of improvements under the hood. So the first thing we added was a new algorithm under the hood to make sure that we were evenly distributing all the data across this large distributed system on DynamoDB. That's available to all customers now. We decreased latency on the ability to be able to change the capacity of your table by 90%. And we decreased read latency, that's getting data out of DynamoDB, by 91% year over year. And all of these improvements were driven by the needs of Prime Day, but now available for all customers. And what that means is that any customer on AWS can run an operation the size of Prime Day literally any day of the year. So just to wrap up, I talked a little bit about data and machine learning, talked a little bit about using machine learning and data on devices at the tactical edge, and then wrapped up with a discussion about how we use data inside Amazon. And with that, I'd like to thank you very much. Thank you very much.
Kevin Granger, do we have any questions in the booth?
We do have a couple.
Okay, please go ahead and read the first question.
What is Amazon's biggest struggle in maintaining data security?
Biggest struggle in maintaining data security. I think it's that we can, security for us is basically job zero. We take it extraordinarily seriously. We have a very, very large data security team, and all they do all day long is improve the security of the platform. So just like the improvements we made for Dynamo for Prime Day, we're continually making improvements like that to the security of our platform. And that means that we hear from customers quite routinely that the data security inside AWS is actually better than they can do in their on-premises environment. We've had that feedback from large financial services, regulated financial services companies like Capital One. And so you can never do too much to improve security. But I don't think it's a struggle for us. I think it's something that we stay on top of. One of the big benefits that we have is that because we have so many customers on the platform, we have millions of active customers every single month on AWS. And what that means is that we get to see security challenges, security risks, security regulations, security compliance needs, security governance needs from a very, very wide range of organizations. Everyone from NASA through to Airbnb. And so we're able to take all of those requirements, distill them down, and make them available to all customers. And what that means is we're almost always a step or two ahead of what most customers need. And we're always working very closely with our customers who are pushing us to improve our security or meet new regulated environments.
Please go ahead and ask the next question, please.
With Amazon's purchase of Whole Foods, what cyber-related challenges do you anticipate during the transition?
Well, I'm pleased to say that the transition is underway. Today is day one of Amazon's ownership of Whole Foods. And already today, we've lowered the prices of Whole Foods produce, common things like milk and bananas and avocados, by up to 43%. We're also making Whole Foods produce available to Amazon Fresh customers. So if you have the Amazon shopping app, you can pull it up now and you'll see Whole Foods products on Fresh. And we're also taking those fresh products and making them available to our service Fresh Pickup, which is where you can order produce and then 15 minutes later just go drive up and pick up and have it deposited to the trunk of your car. And we're going to make Amazon Prime, the membership rewards program for Whole Foods. So it literally is day one today. But in terms of what we're going to do in terms of integration, what we're going to do in terms of lowering prices, improving selection, it's still very early days. But even in this short period of time, we got all of that up and running for today.
We have time for one more question.
Sir, Whole Foods has a program for active duty military who are moving to a new location where they get kind of a starter kit of those things that are commonly thrown away as you move from base to base. But it's only available to those who have a Whole Foods nearby. With Amazon's purchase of Whole Foods, do you anticipate that changing?
Nothing to announce today, but drop me an email and we can discuss it. All right.
All right, we have no further questions.
All right. Thanks, guys. Appreciate it. Oh, wow. You're welcome. Appreciate
Thank
it.
you, Dr. Wood.
Do you have the photo? There you go.
Oh, he's right there. He moved on me. Good.
All right. Thank you. I appreciate it.
Thank you.
All right, next we have the cloud panel coming up.